Hello everyone. I'm making this video to explain a little bit about how to process data from accelerometers and gyroscopes and how to make a GUI. And the GUI that I'll make in this video, or that I'll describe, will be towards analyzing that kind of data. So this is a Matlab file that I made ahead of time. That runs the GUI, so I'll just run it really quickly just to show you how it looks. This is the initial thing that'll pop up. I've made a button that will allow us to choose an Excel file to analyze within the GUI. There are a couple parameters you can change here, which I'll explain later. And then you click Analyze, and it'll take a few seconds and analyze the data and show us how it looks. So we have a bunch of graphs here, and admittedly this probably isn't the best way to display the data, but can be useful at least just to get an initial idea of how your data looks, and you know, it's kind of nice to have it all in one spot. Just a really quick explanation of the graphs. Obviously there are 3 line plots, and these little X and O markers mark the peaks and the valleys in of the plots. So I'll explain how to make a GUI, and I'll walk through the code that I wrote for this GUI in particular and how I analyze the data. Okay, so I'm making this this video in response to a comment that I got in one of my previous videos. So someone asked me to help them analyze this data, sent me a sample data set, and just the context of that data is that I think what they did is they put motion tracking devices on a person and had them walk, and that's what the accelerometer and gyroscope data is capturing, is just the changes in angle of angular velocity and the accelerations as this person was walking. So really quickly, just to show you what that data file looks like as a spreadsheet. Okay, here's what their spreadsheet looks like. There's a few header columns that describe the data, and there's just 6 columns, with 3 columns being accelerometer data and the other 3 being gyroscope data, each having an X component, a Y component, and a Z component in a 3-dimensional coordinate system. And there are 5 separate sheets in the entire spreadsheet. So this first sheet corresponds to the motion tracking device being placed on the subject's backbone. There's one on their right thigh, left thigh, right calf, and left calf. Okay, so that's how the data looks, and I'll show you how to get this data in Matlab and how to process it using what's called a complementary filter, which seems to be a commonly used processing technique to analyze or to work with this sort of data. Okay, so again, here's a file that I ran through ahead of time, or that I made ahead of time, and I'll just run through it really quickly. These first few lines just open up the file and get it into Matlab. So it's in Excel right now. You can import that data into Matlab. I made another video that explains how to do that, so I'm not going to explain this in very much detail. But essentially this does what that button did in the GUI, that basically just allows us to choose the file that we want to look at. This update rate is the frequency that the data was captured, and if we look in the Excel file, it says that the data was captured at 60 Hertz. Meaning that the time between each data collection is 1 over 60 Hertz, which is 1 over 60.01666666 seconds. And that'll come into play later. These 2 variables are part of the complementary filter that I mentioned, and I'll explain that in a few minutes as it becomes more relevant in the code. Here is a nifty little function that I didn't explain in my Excel video, so I'll take a couple minutes to explain it right now. So this function, xlsf info, so it's easy to make a typo. I'll write xlsinfo a lot. but it essentially just gives you the information on an Excel document. So let me clear this workspace and start from scratch. So we need the file name for the Excel document that we want to look at. So I'll just copy and paste this code, choose the file, and then, okay, so we want the XLS F info for the file name of the file that we chose. Now it has two output parameters. This first output parameter is the status of the file that you use as an input. I'm not really sure when this would be useful, but it essentially just tells you what kind of document that you're choosing. So I mean, obviously we know ahead of time that it's an Excel document, so in the code I just kind of suppress that as an output. But the second output is useful. So this tells you the name of each sheet in the spreadsheet. So not only does it obviously just tells you the name, but from that we can determine how many sheets there are, right? So that's what this next line is in the code. It tells you the length of sheet names, which should just be 5 because we have 5 sheets in the Excel spreadsheet. Coming down, this is just pre-allocating the cell arrays that I use in this for loop, and yeah, so I'll just jump into the for loop. So the for loop will loop through each sheet in the Excel spreadsheet document and analyze each one separately, right? So it'll analyze the backbone, accelerometer, and gyroscope data, the one on the right thigh, right calf, left calf. And if you were to have more of these devices on somebody who was walking, like let's say you put them on their wrists or their shoulders, and you had more and more sheets, it would just keep looping until every sheet was analyzed. Okay, so the first thing in this loop is that it'll read in the numeric information from the sheet that you're interested in whatever iteration of the loop you're in. Again, we have this update rate equals 60 hertz, and we have that, which means that the time step between data points is 1 over that update rate. Okay, now we start reading in the accelerometer data. So we have accelerometer data for the X direction, Y direction, and Z direction, again, in this 3D coordinate system. And what we're actually interested in, like the final output of all this data processing, is going to be an angle. So from the accelerometer and the gyroscope, we can determine sort of the angle that the motion capture device is in at a moment in time. And this is the beginning of where we start doing some things to work with the complementary filter. So I'll just really quickly show you what those are in the code, and then I'll explain what the complementary filter is so that it makes more sense. And then we'll come back to the code and move on to the GUI. Okay, so just really quickly, here we're determining the angle about the x-axis as determined by the accelerometer data. Same thing for the angle about the y-axis and then z-axis. And then we actually need to use a for loop to determine the angle according to the gyroscope data. And so just really quickly, the reason why it's important to consider both the accelerometer data and the gyroscope data to determine the angle is that the accelerometer has really noisy data, but it's very stable in the long term. On the other hand, the gyroscope data is very stable short term, but it tends to drift over time. And so the utility of the complementary filter is that you sort of combine both of those positive aspects from the different data capture devices. So you take the long-term stability of the accelerometer, and you take the short-term accuracy of the gyroscope, and you use the complementary filter to combine them, so you get low noise data that is stable over the long term. So that's the point of the complementary filter, and sort of the role that the accelerometer data and the gyroscope data play in the output that we're interested in. Okay, so now I'll explain what the complementary filter actually is mathematically, and that'll make sense of these equations and this for loop. And I'll then show you how to implement that in a graphical user interface to make data processing a little bit easier. So here's the equation for the that incorporates the complementary filter to determine the angle at a certain time point, right? So this is the equation, and I'll just walk through what each variable means. So theta t is the angle at the time point that we're interested in. H is the high pass filter constant that is multiplied by the gyroscope information, and L is the low pass filter constant that is multiplied by the accelerometer information. The gyroscope gives us angular velocity, changes in angular velocity, right? So we multiply the change in angular velocity by the change in time from the previous data point, right? So the change in time between each data point is equal to 1 over the frequency, and our frequency in this case is 60 hertz, right? So that's what delta t equals, is 1 over 60, and that gives us change in time in seconds. Our gyroscope data, again, is angular velocity in units of radians per second. So you multiply those together, you get an angle in radians. And you add that to the angle that you measured from the previous time point, right? So if we say that theta starts at 0, then at the first time point, this will equal 0, and you just add whatever you get from the gyroscope to that, and you just keep adding the changes in the gyroscope information to get your current angle. And then over here, you need to get an angle from your accelerometer information, and I'll quickly explain how to do that. So if we draw a coordinate system poorly, where we have an x-axis, a y-axis, and a z-axis, and let me change colors real quick. We have some acceleration vector, we'll call A. Then we can describe this in terms of its components, right? So if we draw down to the xy plane, right, we have our x component, our y component, and our z component. Okay, so we'll say this is the acceleration in z, acceleration in y, and acceleration in x, right? That's how we've named them in our Matlab file. And so if you want to know the angle about the z-axis that this vector forms, you can consider the acceleration x component and the acceleration in y. Make a triangle. We have a right angle between our axes, and then we're interested in this theta z. Then just from trigonometry, we know that the tangent of theta z is equal to opposite over adjacent. So we have acceleration in y over the acceleration in x. And then we know that theta z is equal to the inverse tangent, or the arctangent, of the acceleration in y over the acceleration in x. Okay, and that's the description of the complementary filter. So I'll show you how we implement that in the code next. Okay, so in the code, we determine the angle from the accelerometer information right here. So the angle about the z-axis, like we just showed, is equal to the arctangent of the y component over the x component, right? Just a quick note about this atan2 function. This is a built-in Matlab function. There's also just a regular atan, and the only difference is that atan will only give you angles between negative pi over 2 and pi over 2, while atan2 will give you angles between negative pi and pi. So it gives us the full range of angles, unlike the normal atan function, which is what we're interested in, right? Because presumably our motion tracking device can measure an angle in 360 degrees, not just 180, right? So we want that information. Now, and then we also have our low pass filter constant multiplied by those angles, right? And we set that constant up here earlier in the code. And we also set the high pass filter constant as well. And just a quick note, these values, these 0.98 and 0.02, those are just commonly used values that I saw online. You can definitely mess with those values, and I'll show you how changing those values affects the results once we finish the explanation of this code. Okay, so there we've determined the angles from our accelerometer information, and down here in this for loop is where we calculate the angle from including the gyroscope information, right? So we have our high pass filter multiplied by the angle determined from the gyroscope, which again is this angular velocity times delta t. And then we add the angle that we determined from the accelerometer information. And so this for loop just goes 1 to the entire length of the data set, and you just keep adding the angle from the gyroscope. So if you're on your first data point, then there's obviously no previous angle to add to. So this doesn't have that term, but for every subsequent data point, we have this term where we add the previous angle to the current change in angle that we calculate from the gyroscope. And that's pretty much it. I mean, then we store that information in this theta x, theta y, theta z. These theta x, theta y, theta z matrices or cell arrays. And then we plot it. So if I just click run, it'll have me choose the file. And there we go. Right, so this looped through each page of the Excel sheet. Okay, now that I've explained the complementary filter, I'll return back to the GUI that I showed you at the beginning of the video, and hopefully now that you know more about the complementary filter, the GUI will make a little bit more sense, and I'll explain more of what it can do. So I just selected a file to analyze. It's the same file we've been looking at this whole time. We have the high pass filter constant and low pass filter constant that are part of the complementary filter equation, and we click analyze, and so I'll just leave that at these default values for now. And we can see the plots. So we plot the three different angles, so the angle about the x-axis, y-axis, and z-axis. Those are the three different lines. And again, the peaks and the valleys, the local maxima and minima in each plot are marked with X's and O's. That was something requested by the person who asked me to make this video. I'm not entirely sure of the usefulness of that in this data. Like, I don't know how this data is going to be analyzed further, but I've found it useful in my own research, and I'll walk through just how to implement that function. It's a built-in Matlab function, so it's pretty simple, and I'll explain that when I walk through the actual code of the GUI. But again, hopefully this GUI makes more sense now in terms of the 5 plots corresponding to sensors placed at different parts of a person's body, and the theta about the X, Y, and Z axes hopefully makes sense as well. Now I'll take this opportunity to show you what happens if we don't use the complementary filter. So the low pass filter again acts on the accelerometer data. So if we set that to 0 and we set the high pass filter constant to 1, it's my understanding that you always want the sum of the two filter constants to equal 1. So if we get rid of the low pass filter constant, essentially getting rid of the accelerometer data, and we click Analyze, takes a few seconds, but now we get what the gyroscope data looks like on its own, and you can see that it starts at 0, but then it kind of diverges for the different angles and drifts over time. So this is that drift that I mentioned in the beginning, and why it's important to apply to include the accelerometer information, because over the long term it tends not to drift. And so you might be wondering, well, why not just use the accelerometer information? And that's because if you don't include the gyroscope information, you only look at the accelerometer, again, we're doing that by setting the high pass filter constant to 0 and the low pass constant to 1, you can see the data becomes incredibly noisy. However, if you look at the start and end points, it tends to stay around 0, so it is relatively stable. And I think just like qualitatively, if you consider the amount of noise in this accelerometer plot, you can see why you might want to weigh the data from the gyroscope more heavily than the data from the accelerometer, hence the big disparity in the filter constants that you use. So 0.98 again and 0.02 are commonly used values online. I think every source that I found used those values, but they're not, you know, it seems to be a pretty qualitative assessment. Like, you kind of just need to determine what your plots should look like and what filter constants are most appropriate for you to use for your system. But I think, you know, using the 0.98 and 0.02, you really don't see very much drift. You know, the plots kind of stay relatively level throughout the course of the data capture. So this seems to at least be a good starting point, and depending on what you're using, depending on your data, you might need to change these around, but I think that's kind of more on a case-by-case basis, and I honestly don't have the familiarity with these kinds of data sets to make any general sweeping statements. But I can tell you about how to make GUIs like this. So before I walk you specifically through this GUI, I'll just show you how to start making a GUI of your own. So one thing that is kind of a challenge when making GUIs is that they're functions in Matlab, meaning that when you run it, you don't necessarily get output data. So it's always good before you make a GUI to just make a script or two that's going to be sort of like the back end of your GUI. Make sure that that works and that it processes the data appropriately before you start making the GUI, because it's going to be kind of a pain to check that whatever processes you run are doing what you want them to do. So just starting from scratch, I'll show you how to make a GUI file. So again, it's a function. You can see that's the very first thing in the GUI file. So let's just call this function new GUI, right? And we'll put some information, and you have to end it. That's just the Matlab syntax. So yeah, so let's just save this. We'll save it as new GUI. If we run it, nothing happens at all, right? So you need to kind of let it know it's a GUI, and you know, the main feature of a GUI is that it has this graphical interface. So In Matlab, you generate that by creating a figure window. So you can do that just by saying h equals figure, and you click run, and it brings up a figure window. So now we need to populate the figure window with buttons and different plots and things that we want to interact with. So if you go to the Matlab documentation online, the way that you add components to a GUI is by using this UI control built-in function. And in fact, if you go back to the GUI code that I already wrote, you can see UI control, UI control, UI control everywhere, right? So that's how I make the button that that lets you choose the file that you want to analyze. That's how I created everything in that GUI. So if you want to make a button, we check the documentation, and it gives you a little like pseudocode on it, like example code on how to make a button. So if you want to make a push button, you need to set the style of UI control to push button, right? So that makes sense. I'll just copy and paste that in here. And we'll call this button, we'll just call it button equals UI control style push button. Okay. Next thing is the string. So this is going to be what the label of the button is. So if we do string, then we say button label, right? Just to be clear. And now we have position. So this is something that I usually probably don't spend enough time getting just right, but you know, it's just the amount of time that you spend on getting this nice is just going to make your GUI look better. So essentially the position that you choose is going to be the X position, the Y position, the width, and the height of the button that you make. So I've found that 200 is a good width and 25 is a good height. I mean, that just kind of looks like a decent size to me. So those are the width and height values that I tend to use. And then the location of the button takes a little bit of like educated guessing and checking. So for right now, I'll just say 1010. And that'll be our first GUI object. So I'll run that code really quickly, and you can see that our push button is right there. And just a quick note is that the position that you prescribe, so the X position and the Y position, start from the bottom left corner of your figure window. So another thing to keep in mind is that instead of just directly just saying that you want a figure, you can actually set the size of your figure, which is what I do in mine, and the position. So this is something that is sort of tricky in that, you know, if somebody doesn't have the same size computer screen as me, the GUI figure window might not fit nicely on their screen. And I'm pretty sure that there's a way that you can kind of define these positions based on like percentage of screen width, but I get the GUI working on my computer, and I tend to only be the only one who uses it, so I just stick with the pixel values. But if you're interested in making a GUI that you plan on sharing with a lot of people, it might be worth the time to plan these positions and sizes of your features more carefully. But again, just really quickly, I'll show you how that changes the figure window. So now you can see the figure window is much larger than it was before, but our button is still in that bottom left corner. So it's always relative to the bottom left corner of your figure window. And of course, you can resize the figure window by dragging the edges as you would normally. And just definitely notice how the button that we made follows the bottom left-hand corner, because that can be tricky when, like, if you change the size of your figure window, but you don't change the position of your button, it could throw things off. But okay, so that's how you make a button. Another useful thing is going to be making areas for you to plot things. So we will need to make axes. And that's actually the first thing that they say. And this actually isn't a UI control, so I made a little mistake. You just use axes, and you say units, pixels, and what size did I use before? There we go. So this is the position that I used before for the GUI in there, and so you can see the axis plot right there. And if we want, we can make the axis really long in the x direction. So it's horizontally stretched out. And again, the size of your axes will depend on the kind of data. So if you have maybe data that's captured over a really long period of time and you'd like to see how it changes, you might want to use a longer x-axis and a shorter y-axis, maybe something like sinusoidal that's carried out for a long period of time. So there's one set of axes, and I'll just make another one right below it. Okay, so again, we have our x position and y position. So our x position can stay the same if we want to have our graphs line up, but we'll need to change the y position. So we'll need to make it, we'll need to lower it relative to the axes that we just made. So yeah, let's just try 30. So that looks okay, and it looks like maybe we could fit another one in between if we wanted to. Again, it's just up to you how much time you spend messing with the GUI. It just depends on how much you care about it looking nice. So yeah, so you can also just add sort of non-functional aspects of your GUI. So if we go back to the UI control, you can have you can add sliders if you want. But another nice thing is just to add text. So I tend to use this as labels for the graphs that I plot. So that's just going to be UI control style text, right? And then you put the position of the text, and then you put the string, basically what you want the text to say. So we'll do position, set some position in a second, and then the string will be, this is a string, right? And you'll notice that I didn't set this equal to anything. You actually kind of don't, you actually don't need to really for buttons and things, but the axes, it's important to set equal to a variable name so that you are specific in terms of what you're plotting to which set of axes. And I'll show you that in a few minutes. But this is our text. We'll say this is a string, and we'll put the position. Let's try to put it over the second set of axes that we made, because it looks like there's a little bit of space above it over here. There's not much room for a title. So we'll aim to put it over the bottom set of axes. And so one convenient thing is, if you want it to be centered over, over the axes, you make it the same width. So the width is 800. I find, again, 25 is usually a good height to use, and use the same x position. And then we want it to be a little bit above the top of the axes. So our Y position is 30 and the height is 250, so it should be over 280 in terms of its Y position. So let's say 290. Let's see how that looks. Yeah, so there you go. And you know, there are settings you can change to like make the font size larger or bold or however you want it. Just, you know, check out the Matlab documentation. I'm not going to go through every single feature, but I think, you know, just going through a few will kind of give you the hang of sort of like how to do this on your own. Okay, so that's pretty much it in terms of how to make a GUI. If you want to keep adding different components, again, it's just a matter of adding axes and adding these UI control features. And you can make them do pretty much whatever you want. Now I'll show you, just using the code that I already wrote, how to make this button, for example, how to make it functional. So I'm going to switch over to the GUI that I already made and just run through really quickly. You know, I have UI control push button. The string in the button is select file to analyze. So if we run this, that's this button right here. Again, another push button that just says analyze. That's this analyze button right here, and so on. And you know, I just have text that labels what the different things are. These UI control components are called edits. So style edit. You put the string as like the default value, and then position as you would normally. And you just keep going like that. I think those are pretty much the only UI control components that I use, and then I have a bunch of axes that I positioned just throughout the figure like this. So something different in these UI control things that I didn't talk about already is this callback feature. So this is what makes the whatever feature, so for example the push button, that's what makes this functional. So you say callback, and then you put this little @ symbol, and then you link it to a function. So the function that I'm linking it to is called getFileCallback, and I define that lower in this code for the GUI. So if I go down here, I've made a separate function called getFileCallback, and it's important you put this these little tildes in there, like tilde, comma, tilde. And I basically say what I want the button to do, right? So this button will call the UI get file, the built-in Matlab function. It'll open up that dialog, allow us to choose a file, define the file name, and then I use this command set app data, right? So this is sort of how you get data out of your GUI. So before I get into that, just to reiterate, getFileCallback is a function that corresponds to the push button that says select file to analyze. So when I push the button, it'll call this callback, where it will bring up the dialog to open an Excel file, save the file name, and use this set app data to really save the file name to this instance of the GUI. Now, set app data requires 3 inputs. So it requires the handle of the GUI, which is just like the what you set the figure equal to. So here it says h, and that's because at the very beginning I said h equals figure. So whatever variable you assign to your figure has to be the first input. The second input is the name of the data that you're saving. So it doesn't have to match the variable name, but it just has to be descriptive. So, you know, we could say, instead of file name, we could just say file, right? And it's the same thing. And then you put the variable that you want to save. And I'll show you why this is useful. Okay, so if we click run, select file to analyze, choose the file, click analyze, it'll run, and you have all this data here, but how do you get that out? Like, what if you wanted to do something else afterwards? Say export it to a different Excel file or something else. that's why this set app data comes in handy, because it allows you to use the get app data function, which requires, again, the figure that you're using and the name of the thing that you want. So GCF just means get current figure. That's a built-in Matlab thing. So this is the only figure that I have open. So if I say GCF, it knows that I'm talking about this one. And then I want the file name data associated with this figure. And it gives it to me, right? This is the file that we chose. And I'm going to use that later in the GUI code too, where it'll allow us to export the data out of the GUI and then work with it further if we want to. Okay, so that's the callback function, but there's this other one called analyze, which obviously is the callback associated with the push button that says analyze. And so this is pretty much the complementary filter code that we went through earlier, with just like slightly different, it's just slightly different in some spots. So one spot where it's different is where we're setting the high pass filter and low pass filter. It gets those values from whatever is entered here in the GUI, right? So the way you do that is by using this get. And so get takes two inputs. So you need to tell it what it's getting, and you need to tell it what kind of data it is. So it's a string, even though it's a number in the GUI, Matlab considers this a string. And you need to tell it, so the first thing is you need to tell it where it's going to get it from. So right here I have HPF, and if you go up, I've defined this UI control as HPF. So this corresponds to this text box. So whatever I've input in this text box corresponds to this HPF object. And so I'm saying from this HPF object, get me the string. And so Matlab considers it a string, but we need it in the form of a number so that we can do math with it. So I use this command str to double. So this is a string to double data conversion function. And I do the same thing for the low pass filter constant. The rest of the code is the same as what I described earlier, until we get to down here. So right here, what I'm doing is I'm setting the axes that I want the plot to be made in. So if I'm on the first sheet, I want it to plot in the first set of axes. So again, now we use this set command. We tell it the name of the figure. We tell it what we're setting. We're setting the current axes to h theta 1. So h theta 1, again, if we go back up, corresponds to this first set of axes, which is this axis right here. And I've defined h theta 2, 3, 4, and 5. So that's one for each sheet in the Excel spreadsheet. And so basically, depending on which sheet you're in the for loop, it'll choose a different set of axes to plot the theta x, theta y, and theta z. And so that's an important reason to always set, when you define axes in a GUI, always set it equal to some variable name. Because you can still get it to display without setting it equal to this, but then you can't really specify which set of axes you want to plot in if you're plotting multiple things. So there's that. We go through all the plots. We plot theta x, theta y, theta z. And I'll come back to this find peaks thing in a minute. And we make the plots nice. We label the x-axes, the y-axes. We provide a legend labeling which plot is theta x, which one is theta y, and which one is theta z. Now down here, we have all this set app data. So this is what really makes the GUI give us usable data, right? So I've named a bunch of these things based on the sheet number and the thing that's being the variable that's being output. So if we do get app data, we do GCF for get current figure. That's the figure that's currently open. And we say, I want the information from sheet number 1, which is the backbone, and I want the theta x information from that sheet. It'll give us this matrix, this 776 by 1 double matrix. And you can do that for all these things. So you have the peaks information, the valleys information for X, Y, and Z all stored. And really the kind of nicest way to do this is if we say Z equals get app data from the current figure. Now we have this Z structure that has everything all in one. We can click on it and open anything we want, and it's just available to us all in one spot. So you can then use this Z structure to do any further data processing from after you're done using the GUI. Okay, so now really quickly, just to end things, I'll explain this find peaks thing. So find peaks is a built-in Matlab function that does what its name says. It finds peaks in a plot. And if we go to the Matlab documentation, actually, let me just search through here. It says find local maxima, right? And it'll tell you the value of the peaks and the location of the peaks. And it can also give you the width and the height, essentially, of the peaks. Now, so really straightforward implementation here. I'm saying find the peaks in the theta x plot for this sheet, whatever sheet we're on, and return the value of the peaks and the location of the peaks, meaning the time point or the index that the peak appears in this theta x data set. But a nice little trick is if you also want the valleys, you just find the peaks of the negative version of whatever plot you're looking at, right? That'll flip it upside down. And you just find the peaks on the negative version, and that'll give you the location, an accurate location of where the peaks are. But you still need to, when it gives you the values, you need to make that -2 to flip it back over. So yeah, that's pretty much everything involved in using the complementary filter, making a GUI that incorporates that, and getting data out of your GUI. I've listed my sources here. These are kind of the 2 most helpful websites I found that explained what the complementary filter was and how to implement it. Again, this isn't, I haven't used the complementary filter before now, so if I've made any like big mistakes that you notice or anything like that, just let me know in the comments, or you know, don't let it slide if it's something bad. But it seems pretty straightforward to me, and I hope that this tutorial at least helped you learn how to make a GUI. So yeah, I've also hosted this code on GitHub. I'll provide a link to that in the description. I'll also provide a link to my tutorial video that tells you how to import Excel data into Matlab, manipulate it, and then export it back out to an Excel file. Yeah, if you have any questions or comments, or if you have a request for a video that you want me to make, just leave a comment, and thanks for watching. Hope this helped.